Swayam Prabha. Digital India. Educated India.
Okay, so this was the last thing which we did in the last class, was estimating entropy change for an irreversible process. And I said I will wind up entropy today. And so we are going to take up the continuation of the class which we had yesterday. So I had said that entropy of mixing of two ideal gases is also a irreversible process for which we need to calculate the entropy change. And I said that I will take this up later on, because mixing means movement of molecules. That means you are having, so far we have been discussing only closed system where there was no permission for matter to enter. So we are not going to take up this right now, but I'm going to discuss this when we are talking about a mixture in an open system. So I have in this PPT or whatever PDF which I'm using, it's actually going to summarize all of the things which is there, whatever expressions are there which we have discussed so far is going to be there in the handout. So you see, these are all the expressions. This is summary of the expressions, summary of all the expressions we have done, summary of the inequalities in the clashes inequality. These have been put here. And this red box, which I have put here for you, if you can see in your screen, is something which I would like you to do after we do the Maxwell's. From Maxwell's, we are going to find out how entropy changes with temperature at constant pressure can be related to Cp by T. Entropy change with temperature at constant volume is related to Cv by T. And from there, we can calculate using the alpha and kappa T, the compressibility constant and the expansive coefficient. We can find out the change in entropy with pressure at constant temperature can be given in terms of alpha into V, and the change of entropy with volume at a given temperature is equal to alpha by kappa. So these are things, this particular thing will I'll be asking you to derive. So these are applications of whatever we have done. All the expressions are summarized in 2 pages, just for your benefit. So these are things which is already done. Now I'm going to do an example. This is also done when we are saying a spontaneous change. I'm not going to do it in that sense, but what we have saying that if you have two boxes of metal connected thermally to each other, so that they are supposed to equilibrate and to have an equal temperature, and they are enclosed in an isolated system, then initially what we have is temperature T1 is not equal to T2. Now the total change in entropy will be given by the entropy change of the box 1 and the plus the change in entropy of the box 2. This we have done in some form in the beginning of the entropy lectures. I had said that how will I find out the total amount of entropy change. Here I had said if this is dq amount is being absorbed by the body T1, and dq is the temperature which is absorbed by the body D2. So now I have to see which is absorption and which is giving out the energy transferred by the box 2. So if I have to find out the total entropy change, from the expression of entropy change, I will find out the direction in which the process is going to proceed. So this we had done it in the previous class, but it is since a repetition I'm taking it up. The total change in entropy will be the entropy change while one box is losing some amount of Q, and the other one is equivalent to this box giving up some amount of heat in the form energy in the form of heat. So The total entropy change will be the sum of change in here and the sum of change of entropy in this box. If I want to find out what is the entropy change, I write down the process being occurring in reversible. I have to make it that it is a reversible thing. I have to make it, though I know it is going to be a direction of spontaneous flow of energy, but I'm going to say that let it be done irreversibly so that I can calculate the delta S. So delta S calculation for the one of the box will be dq1 by T1 minus dq2 by T2. Let us assume that dq1 is equal to dq minus 2. That means whatever amount is being absorbed by the box 1 is actually what is given up by the by the box 2. So if I rewrite this, then I can write down in terms of q1 T2 minus T1 divided by T1 T2. This is something which is very basic. Now, if I want to say the direction of the spontaneous process, that means which will be the preferred direction of heat transfer. Now, you see, if I have T2 greater than T1, then the expression becomes positive, right? This becomes positive. Then this will be a preferred direction. If T1 is greater than T2, then that will not be a preferred direction. So what we have to understand from here, that if T1 by is greater than T2 is greater than T1, that means dq1 is greater than 0. Okay, dq1 is greater than 0. So if I say dq1 is greater than 0, and if T2 is supposed to be greater than T2, T1 is greater than T2, then I say the dq1 is going to be less than 0. So greater than 0 and less than 0 is going to give you the direction of the flow of the energy in the form of heat. If I have greater than 0, this will be the quantity which is going to be absorbed, and this is going to be the quantity which is going to be absorbed. This is going to be negative. So this is going to be the amount which is going to be given off, and this is going to be the amount which is going to be absorbed. So if both the cases heat flows from hot to cold, you can understand which one is going to be the temperature box from which the heat is going to be transferred. Now tell me which is going to be the box from which heat is going to be transferred, so that it will have an entropy positive. Tell me. I'm saying the T1 are not equal, is not equal to T2. In this diagram, which one is going to, heat transfer is going to take place from which box to which box?
From T2 to T1, ma'am.
Yes, from T2 to T1. So the heat transferred from this to this. So you can find out the direction of the heat flow from the expression which we write down and put in the condition that you get a positive value of entropy change. Okay. Okay, now this is another example which is very relevant, and on the basis of this we are going to introduce certain new terms. Calculation of entropy change for a spontaneous process. One of the spontaneous process we have discussed previously is the Joule-Thomson expansion of an ideal gas. If you remember, the gas was enclosed in one of the bulbs, and the other connected to another bulb which was in vacuum, and it was separated by a stop cork. Okay, so if the bulbs were of the same size and I'm allowing the taking off the stop cork, what we had noticed that the volume is going to double, but it was carried out isothermally and in an insulated container. So we had, if you remember the Joules experiment, it was an expansion of a gas from where we deduce that internal energy is not, it does not change with volume. That is the error experiment. That experiment I am talking about. The Joules experiment of expansion of an ideal gas. Two bulbs are there. Let the bulbs be of the same size. One is containing the gas and the other is vacuum. They are connected together by a pipe which is having a stop cork. Now you remove the stop cork entire system is placed in a container where there is no heat exchange from the surrounding. So it's an adiabatic insulated container you have, and I am saying that the expansion is taking place isothermally. There is no change in temperature. So if I have to write that, I can write down like this: 1 mole of the gas, suppose it is there. The volume is, if the two containers have the same volume V at some temperature T, after expansion what you have, the condition is adiabatic. After expansion, what you have 1 mole of gas. Now the size is doubled, 2V is the volume, and the temperature is remaining constant. So if the temperature is remaining constant, it's an isothermal condition. So U will be equal to 0. Okay, there is a volume change, so there should be a work done, but there is no exchange of energy with the system and the surrounding. Q is equal to 0. So obviously the Q becomes 0 here, and work done, in spite of having a double in size, we do not get the work done reflected here. So what we do is, this is a spontaneous process. This is going to occur without any constraints or without any force being applied by us. So this is going to be spontaneously occurring. So what we do, we try to chalk out a reversible path. For reversible path, what we do, we go from here to here back. So the back one is what? I compress the gas back isothermally and reversibly. Okay, isothermally and reversibly. What happens? Since it's a container which is having thermally insulated, there is no Q exchange with the surrounding. There is no Q exchange with the surrounding. Okay, but we have a volume change. Right? So if I have only volume change, and I'm saying there is no reversible amount of the heat exchange, then ideally I should get a 0 value of entropy change, right? But we can understand, when we are expanding the gas to a bigger size, the entropy is supposed to increase, right? So if the entropy is increased but from the expression we have, we cannot determine what is the entropy change, because it's a thermally insulated container, and even if I carry out a reverse process isothermally, the Q is equal to 0. Here Q is equal to 0, U is also equal to 0. So how do I find out the entropy change? So I do a condition of reversing the gas back to its original position by carrying out a compression. And what is the compression I carry out? I carry out the compression from 2V to being 1V. Okay. So if it is an isothermal, if the gas is taken to be ideal and it's an isothermal condition, what will be the value of delta S? dq reversible by T is 1. What is the process, the value you should get? But since in this process it's carried out isothermally, so delta U is 0. So Q will be equal to minus W. So minus W expression you have for an ideal gas. And for the ideal gas, what it is, what for n moles of gas, it is nR ln V2 by V1 into T. Now here you have a T, the T gets cancelled. So what you have the expression of the entropy is 1 mole of gas, so N equal to 1 R V delta V by V integrated over from 2V to V, which is there in the expression. If you put it, what do you get? It will be R ln V by 2V, right? So if I have R ln V by V2, then I can rewrite as ln R ln 1 by 2. But what we have carried out, I'm trying to find out the entropy change for the expansion. But what we have carried out is a compression process. So whatever I get as the entropy for the system, it should be minus the whatever the back one direction which we have taken. So if I take it in the reverse with a minus sign, then it becomes R ln 2, which is greater than equal to 0. So if you have understood what we did is we calculated delta S for an irreversible process. We chalked out a reversible path to determine what will be delta Q reversible by T. Okay. Here I have, since I have done an isothermal expansion, here I have taken that dq reversible is not equal to 0, but initially the dq reversible was 0, right?
Yes, ma'am.
So I hope you have understood that we chalk out a reversible path. Here we have chalked out a isothermal reversible process of compression of the gas instead of the expansion, so that you get back the original state of volume and temperature. And if I have to carry out isothermal, then the work is done against what? How do I get the Q? How in the isothermal Q is not equal to 0? What is equal to 0 in isothermal? Delta U is equal to 0. In isothermal process, the delta Q will be equal to the minus W, right?
Yes, ma'am.
Okay, so if you have understood this, you please remember what we have done here. What we can write in this expression is delta S equal to ln T to 2 to the power R. Can we write that? Can we write that?
Ma'am, can you
Delta
repeat?
S,
Yes, ma'am.
delta S, here I have got the expansion of a gas to double its volume. I can rewrite this as ln T to 2 to the power R.
Yes, ma'am.
Okay, and R is what? Cp minus Cv. So what will be the value coming to for a monoatomic gas? What is the R? Value of R for a R is independent of whether it's monoatomic or
Yes, it is
diatomic.
constant, right?
What is R here? What is the value of R?
It 0.082. 8.314.
8.314. So it's a decimal. But we are going to get something very close to this when we write down the Boltzmann equation for the expansion of a gas, of ideal gas. And why is the Boltzmann equation important? That I will take up in a while. So if I want to represent the entropy change in a TS diagram, how do I do that? Suppose I take the Carnot's engine, I want to draw a TS diagram. So far we have only done PV diagram. Now what happens if I transform the scale to TS for a Carnot cycle? This is not S, this is C. Show for a Carnot cycle that the on a TS diagram and identify the heat transfer at both high and low temperatures and the work output from. This is a question I've asked. You find out the work output from the cycle, you identify the amount of heat transferred from the high temperature and the low temperature. So let us see what happens. I have this T and this S as the two excesses, and I want to find out the Carnot cycle, how it will look in the TS plot. So TS plot, first step is from 1 to 2 for a Carnot cycle. If you remember, first step is a reversible isothermal heat transfer, right? That is isothermal expansion, right? That is the process in which you have a heat transfer to the system from the surrounding, right? Please say yes.
Yes, ma'am.
Okay, so for the first step, it is reversible isothermal expansion. In the first step, we have going from point 1 to point 2, the reversible transfer of heat from the surrounding to the system, from the reservoir to the system, right? So from going from point 1 to 2, I mark this temperature as TH. This temperature should be TH, and it's isothermal. Going from T1 point 1 to point 2, the temperature will remain constant. And what will be the entropy change for that particular process? What will be the entropy change for the particular process? Here you have the delta Q is equal to, it's a reversible process, reversible cycle. So what you have, delta S equal to Q reversible by T, right? So Q reversible by T, if I write down delta S, then what will Q become? T delta S, right? S equal to Q by T. So Q will be delta S into T, right? And what is the delta S corresponding to? This is the 1 delta S and this is the 2 delta S. So the area under 1, 2 and AB, this area is going to be the amount of, will give you the measure of the heat transferred isothermally, right? Now I go to the point 2 to 3. What was that process? That was an adiabatic process, adiabatic expansion. So adiabatic expansion, the entropy change is 0. So entropy change is 0. That means the entropy of 2 and 3 places will have the same value. So I can join a line. Now going to the isothermal heat transfer step again. Here you have the isothermal compression, reversible isothermal compression. Here what you have, the system transferred some amount of heat to the surrounding. Okay, so and that we had called is the QL or QC, whatever. So if I have to find out what is the QC, then that will be again T into delta S. What is the delta S which we have now? Delta S is going to be from S3 to S4, right? So the total amount of heat transferred, will be the area 3, 4 and AB, right? Now final step is what? Is a reversible adiabatic compression, and adiabatic compression means the entropy does not change. So you will have a constant line. The entropy of S1 and is equal to S4, and so is S2 equal to S3. So if I join the lines, I get the area, and this area is the net work delivered by the system when you are having the Carnot cycle. So 1, 2, 3, 4, this is the area, the shaded area is the net work done from the cycle. From just using the values of the, if you are given such a diagram and the values are given, you should be able to find out what is the area in not even going into the calculations, if you know how to draw the diagram, right? The amount of heat transfer also you can find out. 1, 2, 2 and AB, this area, this entire area will correspond to the heat which is transferred to the to the system from the surrounding or the reservoir. And what is the heat which is rejected to a low temperature reservoir? It is nothing but this one, 3, 4 AB. So if the values are given to you on the plot, then instead of going to through the calculation, you can find out what will be the net work done and the total heat transferred at high temperature and low temperature, right? Okay. Now, this is the last topic I'm going to take up in entropy. I hurriedly made these slides. I have not even made the copy pasted from places. So Boltzmann's equation of entropy is something which is, I think, when you are in second year course, since eventually you are going to do statistical mechanics in your third year, fourth year class. So it is always better to understand what we are going to, what we have in the Boltzmann equation of entropy. This is the most relevant equation which, as far as thermodynamics is concerned, for a chemist. Boltzmann equation, what it does is relates the macroscopic property of a system to the microscopic properties. Okay. When I'm talking about a macroscopic property, I'm talking about entropy. So the entropy is the macroscopic property, and how it relates that to a microscopic property, it relates to the omega. This omega is the number of microstates a system can have, and this is it is proportional to the ln of the microstates we can have, and the proportionality constant is nothing but the Boltzmann constant, 1.38 into 10 to the power minus 23 joules per Kelvin. So this is the equation which relates the macroscopic property entropy to the microscopic properties of a system. When we are talking about chemistry, we are dealing with molecules, ions, atoms. So we need to know the microscopic details. So for relating that, we generate what Boltzmann generated is a term which is omega. This is the probability of the microstates that is occurring, most probable microstate. And what is the microstate? Microstate is a instantaneous condition of the molecule. In terms of entropy, what do we understand? Entropy is the dissipational loss of the heat, which is not available for dispersion of heat, which is not available for work. That is the measure of entropy. Here we similarly we have, it is the dispersion of the energies in the microstates. Okay, how the energy is distribution in the microstates. So actually we have entropy associated with two types of changes, like if you are having a positional disorder or you have a thermal disorder. Positional disorder means the distribution of the particles in space, means how the microstates are existing in the space, and the other one is the distribution of energy in the various states. A distribution of energy in various states is something a little complicated. We're not going to discuss it right now. We are just going to list out what are the things which can affect the entropy. See, if the number of microstate, I said microstate is the condition in which a molecule can be existing in the highest probability. So it's a measure of the probability of the microstate existing for a particular system. And as the number of microstates increase, the disorderness increases. Okay, the number of microstates can be increased by two ways. If the volume is increased, because it is a property which is say extensive. So if you increase the volume, what you have, the microstates associated may be increased, and if there is an increase in temperature. Okay, increase in temperature is going to be coming from the thermal disorder, the distribution of energy states among the molecules. And here what we have, a positional disorder, is how the distribution of molecules in the microstates, or we can say how the microstates are distributed. Okay, so what is the microstate? Microstate is an instantaneous picture of the state. Okay, the greater the number of the arrangements possible for a state, the microstate, the greater is the entropy. Okay, so suppose I have the same Joule's expansion experiment done in a manner where I'm looking into the molecules. Okay, I have 4 distinguishable particles sealed in one side of the bulbs. Okay, and one side of the two compartments, we had said that one of the compartment was completely empty and another one had the gas. And I say the number of particles or molecules in that gas is, let it be 4 molecules. Let it be 4 molecules which are distinguishable. Here I have marked them with various color. One is red, one is blue, one is yellow, and one is purple. Now suppose this compartment is open. Now it will redistribute. And how in this redistribution, we are actually going to look how the single distinguishable particle will distribute themselves. We are looking into the disorder in space. Okay, and that gives you the instantaneous picture of a molecule in that state is the microstate. Understood? Am I clear?
Yes, ma'am.
So instantaneous picture of a position of a molecule in that system gives you one microstate. Okay, so let us move into the next one. Yes.
Ma'am, by microstate, position of microstate, do we mean that we are observing that how the energy for all the particles is there for a given instant, like that?
No. See, I have told you we have disorders of two types. We have positional and thermal entropy associated.
Yes, ma'am.
Okay, what we had done in Joule's experiment, we did not talk about temperature, right?
Yes, ma'am.
Temperature also contribute to the disorder, but temperature quantification of temperature is going to be more complex, and you need to do the statistical mechanics class for that. Okay, it is how the energy is distributed in various molecules. You understand? You come down to energy and how the distributions are going to take place, and each of the
Yes.
molecules have energy states. Okay, you have vibrational energy state, you have rotational energy states. So you have to go into the micro picture of you have to understand the quantum mechanics of the molecule to understand how the energy distribution is going to take place.
Yes,
For
ma'am.
now, we are going to say only that temperature is going to contribute. We know from before that if you increase the temperature, the entropy is increasing. Okay.
So, but
Ma'am,
ma'am,
is it
here,
something related to kinetic energy of the particles, which increases with increase in temperature and hence randomness increases?
No. When you are talking about the distribution of molecules, whether it is thermal or any other form of excitation, it is going to obviously we have to leave the classical mechanics and move into quantum. Okay, we have to move into quantum because in quantum mechanics you have discrete energy levels, right? They are
yes, ma'am.
quantized. And these
Yes.
energy levels, how they distribute within the molecule is what is the contribution we are talking about. Am I clear?
So,
Yes, ma'am.
ma'am, basically here we are saying that as we increase the size of the ensemble, the entropy will also increase.
Yes. That is the macroscopic thing which you can think, right?
Yes.
So if I don't increase the ensemble, if I have the different combinations of a same ensemble, the different configurations also give me
A
different
different,
states.
yeah.
So that is what we are looking into. We are seeing how the positional difference is going to contribute to the increase in entropy.
Okay, so the reordering of the same number of particles, the reordering of the same ensemble gives us the positional disorder, and increasing the number of particles gives us a thermal disorder, like that.
Increasing the see, it is an intensive property. If you are increasing the number of particles, you are obviously increasing the number of entropy and the number of microstates.
Yes, ma'am.
But what I'm saying here is how the microstates is something, how the distribution of the molecules are in space. And when I'm talking about thermal disorder, I'm talking about how the energy is distributed in the molecular states. states, various energy levels in the molecule.
Yes, ma'am.
Okay. So what I'm, if you see this example, I think it will be clear. So I'm talking about only positional distribution of molecules. I'm not talking about the energy distribution in the molecules. I'm not talking about, but we both, before we do this or talk about this, we already know that temperature and volume will contribute to an increase in entropy. And when we are increasing the volume or we are increasing the number of moles, we are increasing the entropy anyway. But for a given system, how the disorderedness is connected. If I have only 4 molecules, this is what I was trying to say. If I have only 4 molecules, gas molecules in the Joules experiment, okay, that time I had said I have no temperature contribution, okay, I have only volume contribution. Just now we had done that expression, delta S equal to R ln 2, we just now had done, right? Okay.
Yes, ma'am.
Now I'm going to correlate that experiment with this one. I've said the gas is expanded to double its size. So this is the double size I have. Now, how is the energy being, how is the molecules being represented in the two balls is how I'm going to look into the configuration and the microstates. That is the configurational microstates I'm talking about. Okay. So this is one state where all of the 4 molecules is in one compartment, right? And how is
Yes.
it this going to look like? Say they are distinguishing particles, but actually they are not, right? So I'm marking them in red, yellow, pink, and purple, whatever. But actually, we cannot distinguish 4 particles of gas. 4 gas molecules cannot be distinguished. So I can have all the 4 particles here. Initially, I said all of them were in this or in this, one of them, and the other was vacuum, right? That was my initial condition.
Yes, ma'am.
And however I put, however I decide, the molecules are randomly moving. Gas molecules are in random motion. Whatever I put, all the 4 molecules will be here. So I have one energy state, microstate, corresponding to this state. Now let us see. If I have one molecule in the one of the globes and other is having only 3 molecules. Right? This can also be a position at any instant of time. How the picture is looking, how are they distributed? This is the spatial distribution I'm looking into, and each of the configuration will have some amount of micro, that is the microstate we are talking about. So you understood what are the microstate I'm saying?
Yes, ma'am. But in practically, we'll have to exclude some of these, right? Because repetitions will be there. Like the first two are basically identical, right?
Yes, first 2 are identical, but the size, the probability of occurrence is not going to be the same. If this is going to occur once, this may also occur. The first, initially there was no possibility of this. Initially there was no possibility of having the gas in the other side, right?
Yes, ma'am. No, I'm saying that if the particles are identical, then we might have to exclude some of the microstates because it will get repeated.
No, we will say that those microstates are equivalent.
Oh, okay, okay, okay.
Okay, because
Yes.
see what I have done here. I have done only one molecule in one of the globes. Initially it was like this. I open the pinch cock and I imagine one of the molecule going into the other globe, right?
Yes, ma'am.
Similarly, I can have one pink going, one red going, or the one of the yellow going, or these are the 4 possibilities I have. Only these 4 possibilities.
Yes, ma'am.
Okay. So, what is the condition if I have 2 of them going and residing on the other side? then two of the either blue and red, blue and yellow, and pink and purple one side. I reverse this. This can be another position, and I then reverse the order. These combinations can be also changed. So this way, if I want to do the permutations, how many I can get? 1, 2, 3, 4, 5, 6. 6. So I can get 6 microstates here, right? Here I can get 4 microstates, where they are all of equivalent microstates. And again, I can have a similar thing where I have on the other globe, I have 3 and 3 and 3. Okay? They are again equivalent to this one. But if I clearly identify left hand side and right hand side, then they are going to have unique 4 sets of microstates which are equivalent. So the microstates I get here is 4, which is equivalent. Here 4, which is equivalent. Here 4, it is 6, which is equivalent. And here 1 and here 1, unique.
Yes, ma'am.
Now, if you say that instead of 4 molecules, you have increased amount of molecules. When you talk about a substance which is in a chemistry syllabus, we talk in terms of Avogadro numbers, right?
Yes, ma'am.
So in Avogadro numbers, how do you find out for such a large number of molecules? Is from here what we are going to find out is totally how many microstates we have here. Total count is how many? If they are distinguishable, 16. And initially, how many I had?
1.
1. So if I want to write down the delta S, I can write down the delta S, the microstate which was final divided by the microstates of initial.
Yes, ma'am.
It's nothing but 16 by 1.
Yes.
Understood?
Yes.
So this is the generally when we write down, if you understood, if I just want to give you a flavor, I'm not asking you to do anything on this. You should know that Maxwell's Boltzmann's equation is a very famous equation in entropy. All your say statistical mechanics, all chemistry is standing on this.
Ma'am, can you go ahead 2 slides?
Which one?
Next slide. Yeah,
This
this
one?
one. So, ma'am, here, yes, ma'am. So, ma'am, in this figure, if we see, it kind of looks like that bell curve type of thing, right? So, can we say that at any given point of time, the expected value of the system will be the third one, the expected
No.
microstate of that system? If it
No,
is, if everything
you
is
have to find
constant.
out. You have to find out, and you have to find out the most probable, the highest number of microstates that is going to exist. So, which is going to be the most probable state? From here, the most probable state is this one.
Yes, ma'am. So the peak one will be the most probable state, right? In
Most
any
probable
type
for
of
any
configuration.
for any distribution. The peak which will where you have the maximum amount of microstates is the most probable state which is going to be there. And if you increase the number of microstates, if there is a large number of molecules, then there will be large number of equivalent states which you can generate into
Yes,
10 to the
ma'am.
23 order, right? So if you are increasing the number of molecules, you are indirectly increasing the possibility of their arrangement. These, each of them are a microstate. So their number of microstates will be increased much, though they may be equivalent.
Yes, ma'am.
It may be equivalent. Suppose you have experiment a thing which you have 20 times you are tossing a coin, and 10 times you are getting a head. But the 10 times is remaining the 10 times. But in this 10, all the 10 coins may not be having the head. You can in between change some of them and make the tail and some other making the head. Understood what I am saying? Suppose you have 20 times a tossing of a coin, you can get head or tail. I said I got the result as 10 heads in the toss. Okay. Now in this 10 head, I can have other conditions, equivalent conditions where I can change some of the tails to head and still retain 10 number of heads, right?
Yes, ma'am.
So these are this is how they are known as equivalent microstates. So what I am trying to say that when you talk about Boltzmann equation in entropy, you are correlating the microstates, which is a microscopic property, to a macroscopic property like entropy. It is so fundamental equation that you can correlate a microstate with a macrostate, which is usually otherwise not possible. When you do engineering, you do only about micros. You do not macro. You do not even think about micro. But when you do chemistry, you have to think about micro.
Ma'am, is
Right?
energy also a macroscopic property?
Energy.
Is energy also a macroscopic property?
Energy is a universal property. Now you have to define whether it is classical way or in quantum mechanics way.
Okay.
Energy you have to see, like here we have the position in terms of position of the gas molecule. We can have in terms of the velocity of the gas molecule. We have to have a criteria in which according to which we are doing the positional distribution. Because
Yes,
gases are
ma'am.
moving, we can have a measure of the this many molecules are having such amount of velocity and these many are having velocity depending on whatever criteria we are choosing. So we are choosing the distribution of the microstates based on how the molecules are going to rearrange themselves in the two possible conditions which you have. So in this equation, this is the max, this is the omega represents the most probable state which for that particular system. That will give you the entropy. Okay. This is the measure of
Yes.
the microstates, and this is going to the most probable microstates into the ln of that into the Boltzmann constant give you the measure of the entropy of that particular state. And for this sort of a expansion, we have done the numerical as to find out what will be the number of microstates here. It is 16, and what was the possible when it was before expansion, it is 1. So I can get how the entropy change is taking place. Here I have written down the entropy change, and here I am talking about the entropy. Okay, entropy of a system. Understood?
Yes, ma'am.
So this will be taken up much. I just remember that when you are asked that do you know this equation, at least say yes, you have heard it somewhere, because you're going to do the statistical mechanics course in detail. Okay, now I would
Ma'am,
like,
uh,
yes.
ma'am, so in quantum mechanics, like we define we solve the Schrodinger equation basically to predict all the properties of a given particle. So, can we? Is there
What do you
anything
find out?
equivalent?
What do you find out in quantum mechanics? You
We
find out
we
the
can,
quantized states. You find
yeah,
out the
the energy
quantized
states
energy
of the
states
particle.
of the
Yes.
particle, right? But here we have not even talked about the energy, because energy is going to be related to temperature. Okay.
Yes.
And the distribution of energy in a molecule is you cannot discuss this until you have done a course on quantum mechanics, because you have to know. I don't know whether you are doing in physics. If you are doing quantum
Yeah, ma'am.
mechanics,
We are right now doing quantum mechanics.
you are doing quantum mechanics, so you have now you have been taught what is rotational, vibrational level, what is
No, ma'am. That statistical part is not yet done, but it is. I think it is there in the syllabus.
Okay. I don't think you will take up statistical part. And you will not talk about energy diagram, because excitation through thermal or through other ways of excitation, energy gets distributed in the various quantized energy states which we have. A molecule will have certain quantized energy states, and the energy is going to be distributed in the various energy states according to the temperature. Okay. So I will not discuss this any further. It is a very basic elementary explanation of whatever we can relate the entropy to. So only thing is, if you have understood a little bit, that is sufficient for this class. So I will take a few examples and then end this class. 1 mole of hydrogen, this which we have done already in the class, in the previous class. Mixing is another irreversible process. I want you to see these examples and find out. This is also something which we have, which can be done. You have to go through this. You have to go through. Let me take up something which we can talk in the class. Okay, let us talk about this. In a Carnot engine, what is the sign of entropy change of a hot reservoir? Greater than equal to 0, less than equal to 0, or equal to 0? I want answers.
It will be less than 0 because heat goes from the hot reservoir to the cold reservoir.
Nishant is going to
It is
answer.
from the hot from.
I'm not asking you. You are. What's your name? You are
Suprita.
Divyangana. Huh?
No. Suprita.
Suprita. Okay. Suprita, I don't want to hear from you. I want to hear from Nishant. Nishant, is he there in the class? Anybody else? Lekha? Aditya? I want answers from the boys. Answers are already marked. I want you to answer with logic. Total pin drop silence. Divyangana?
Yes, ma'am.
Answer it.
Ma'am, which one?
The question is in front of you. You are not in front of the computer. Yes, hurry up, please. What is the sign of the entropy change of a hot reservoir during one cycle?
Ma'am, can I answer?
Yes. You will answer, nobody else will, because all of them are not in there. They are busy playing something. How many of you are playing computer games while we are having this course on? First test will reflect. Yes, Suprita.
Yes, ma'am.
Who was answering? You were answering?
Yes, ma'am.
Ma'am, me, Aditi.
Aditi. Okay.
You told me not to
So,
answer.
Aditi, tell me.
ma'am,
Your dog is barking.
yes, ma'am, like in my background there is noise, so please ignore.
Go ahead. Go ahead.
So, during first cycle, the entropy change of the hot reservoir would be negative because heat is transferred from hot reservoir to cold reservoir, and hence entropy, that's why that q will also q will get negative. Temperature is ma'am.
Q will get negative. How will Q become negative?
Ma'am, because temperature is like flowing from high temperature to the low temperature. So
High temperature to low temperature.
yes, ma'am. The like heat transfers from the hot reservoir to the cold reservoir. So delta
Reservoir
S is
come-
equals to Q reversible by T.
where is the cold reservoir coming? Entropy change of a hot reservoir. I'm talking about the hot reservoir during one cycle. Yes. Anybody else? Ipshita? Shuprita, you answer. Let me hear what you have to say.
Ma'am, the heat is being released from the hot reservoir, so that's why the sign of Q will be negative, right? dQ will be negative. So that's why it should be negative, the sign of entropy.
Acha, tell me then, any exothermic process will always have
Yes,
the
ma'am.
Q is negative, right?
Yes,
Yes,
ma'am.
ma'am. For an exothermic process,
So
will be
that means
negative.
any exothermic process will never be spontaneous.
No, ma'am. It's not like that.
It's not like that.
No, I mean freezing occurs, so it should occur. So it's not always not
Then what is happening?
spontaneous.
Then how is it occurring? If you have an exothermic reaction, the heat is given off from the system to the surrounding. So the process should be having a negative entropy. So how can that process occur?
Ma'am, it will not be a negative entropy. The systems, like for example in freezing, the system's entropy, it is basically a phase transition. So the system's entropy will be negative, and the surroundings entropy will be the negative of that negative. So the total entropy of the universe will be zero. So
Yes. So we
it
have to
will go
look into
towards
the
the.
total.
It will not be negative. It will just not be positive. So it will occur.
It will occur because when we are looking into the total entropy of the universe is what we have to report. Because there are a
Yes.
number of processes where you can have in our body, if you are seeing biochemical reactions, certain biochemical reactions do have negative entropy, but overall system which is going on is going to be equalized, and the system has to have a entropy which is increasing. Okay. And when we are talking about a Carnot's engine, it is has to become equal to zero because it's a cycle, right?
Yes, ma'am. Ma'am,
Okay,
so
next
here
what?
for the first one, the answer will be negative only, no?
Yes, we have said it is because the energy is flowing out of the reservoir. But this is a
Yes.
hypothetical question. You remember the temperature of the reservoir does not change. It is supposed to be
Yes,
huge.
ma'am.
Okay, this is a hypothetical question. It doesn't mean anything. But the only thing is, if there is a finite amount of heat which is given out from a certain source that is not even identified as a reservoir. Okay, this is a hypothetical question. So, since the heat is given out of the reservoir, so the entropy is supposed to be decreasing because the number of microstates is going to decrease. So, whenever you are talking about a decrease in temperature, is automatically an amount of disorderedness is also decreasing, and the disorderedness is related to the disordered positional distribution of various microstates in space. Or we can say the snapshot of each of the state of the molecule in space is corresponding to microstate, and you may have equivalent energy microstates, but and the probability will be depending on how many of that such equivalent are going to exist. Okay, and the highest probability is what is going to occur. Anyway, next one, what is the sign of the entropy change of a cold reservoir? This is obviously the corollary of whatever we had done. We cannot have the temperature change of a reservoir, but still, since it is going to be absorbing energy, it is going to be having a positive entropy, right? These
Yes,
are
ma'am.
okay, and compare the magnitudes of the two. Only the magnitudes. Don't talk about signs. What about the magnitudes? It's a Carnot cycle.
The magnitude would be equal of both.
Yes, otherwise how will you get a zero? Understood? Eventually it's a Carnot cycle, reversible cycle, it has to come to zero. So magnitude wise they should be equal and opposite. But we are talking about magnitude, we are not talking about sign. The values should be equal, right?
Yes, ma'am.
Okay. Okay, I will take up the criteria for spontaneous change from the next class. So let us end this class, and if you have any questions, I'm going to answer. Any questions from so far whatever we have done, because we are going to apply in the next class, we are going to apply the second law to predict the criteria for a change of state. We had said that one of the parameters we have already discussed, that a change of state for an isolated system is going to be such that it will continue to keep changing until it reaches the equilibrium where you have reached the maximum entropy. One of the things we have first topic of that discussion, criteria of spontaneous change, is already discussed, and I hope you will remember that. And we are going to find out the condition for equilibrium and the direction of the spontaneous change. So the direction of spontaneous change is going to continue for an isolated system towards whichever process is proceeding, as long as the entropy is increasing, and it will stop to occur when the condition of equilibrium is reached.